Uh,
Good afternoon and welcome to Hydromantis webinar. My name is Rajiv Goyal and I have with me here Spencer Snolling and we'll be conducting the webinar. So today we have chosen the topic to show you how you can use drying and incineration unit processes while modeling your uh, solid processing and in a wastewater treatment plant. And we will be highlighting some of the key features of these two specific models in GPSX. So the agenda for today's webinar is we'll be showing you some of the new unit processes that we have put in GPSX 8. And in fact, the drying and incinerating unit processes are part of the version 8. So if you have previous versions, then you will have to actually upgrade it to version 8 to use these two unit processes. We will then touch upon some of the concepts of drying and incineration, give you a little bit of introduction, provide you with a model overview, and show you some of the desktop examples using these two technologies. Finally, we'll come to a question and answer session. So we may not be able to address all of the questions, but if you have any questions, please do type them into the chat box there. And at the end of the seminar, if we are not able to answer those things during the seminar, then we'll come back to you after the seminar. So first of all, just to highlight some of the new processes that we have in GPSX 8. So we have made a number of new additions to model the liquid treatment as well as the solid treatment. And in fact, there are 13 new unit processes that you will find in version 8. So this actually extend the capabilities of GPSX with respect to analyzing new technologies for wastewater treatment plant, and in fact extend it to include some other solid handling facilities like sludge drying and incineration. So today our focus will primarily be on sludge drying and sludge incinerator, and so we'll get started on that. So just to kind of give you a little bit of a background about sludge drying, and we know that there are quite a lot of challenges that we normally typically face with respect to solid disposal from wastewater treatment plants. And in that direction, the sludge drying could be an attractive alternative to find out some new options for disposal and the treatment of the solids that are being generated at the wastewater treatment plants. So sludge drying is in fact a volume reduction technology. So what we are essentially doing is we're trying to remove the free water that is there in the sludge and use evaporated basically to reduce the volume of the total solids or the total sludge that is being produced from the system. So it doesn't do anything with the solids, but mostly it removes the water from the system. So what it does is by removing the water itself, we are actually increasing the calorific value of the sludge or the solids or the remaining product, and that becomes much more amiable for using it to take it for further incineration, or we can use it for other disposal routes like coal-fired power plants, cement industries, pyrolysis. And in fact, since it is a thermal process, depending on the time and the temperature that is used in sludge drying, the product that comes out from sludge drying is pasteurized, it's hygienic, and a stable product that can be used for agriculture reuse and landfill. So it in fact opens up several routes for disposal of the excess sludge that is being generated from the wastewater treatment plants. There are various different type of technologies which can be based on convective dryers, convective principles, or conduction, or a combination of the two. But essentially, the main principle is using the heat transfer to remove the excess water or the free water from the sludge that is being generated in the system. So if we look at just the model, and in fact, we cannot go through all the equations that are underlying equations, but we'll just give you an overview with respect to the construction of the model, what you can expect, or what type of analysis you can do using the model. So first of all, looking at the mass balance, we can see that there is an inlet for the dryer object where we are feeding our sludge solids. And there are two outlets. One is for the dry solid, and the other one is for the water vapor. With respect to the wet solids, the user can input the information with respect to the flow rates, the total suspended solids, and various other components that are there in the sludge manually, or these can be actually uh, kind of retrieved, or they can be received from the upstream processes automatically, as happens in the process simulators. So once we look at these kind of three streams, then essentially the model, what it tries to do is it looks at different components and tries to establish a mass balance with respect to each and every component, and in fact the total masses that are being fed into the system, and tries to find out the magnitude of the water vapor, or the amount of water vapor that will be generated or that needs to be evaporated, and also estimates the dry solids and the composition of those dry solids with respect to various compounds that are coming from the feed. So the purpose of this is essentially, if we are given with a wet solid that are coming in, then we can estimate the amount of dry solids that will be produced, and the composition of the dry solids, and the amount of the water vapor. In addition to doing the mass balance, we are also doing thermal energy balance across the dryer, in which case we are also taking into account, of course, the external heat that is required to be inputted to the dryer for using it for evaporating the water that is there, and also a function that can be used for calculating the heat loss from the dryer. So in fact, it becomes kind of a simple balance which requires the thermal energy of the wet solids that are being fed into the dryer, plus the external heat that is equal to the dry solids, the thermal energy of the dry solids, plus the thermal energy of the water vapor, plus the losses that are happening in the dryer. So as I said, there are various technologies that are there for the drying. So we are not specifically modeling a specific kind of technique, but we are allowing user, it's a general model which can be used for various across the different technologies by adjusting some of the different factors with respect to, for example, the heat loss or the efficiency of the energy uses in each dryer. So just to show you some of the operational variable that we have for sludge drying unit process. So first of all, we need to get the information about the temperature of the feed sludge. So there are two processes or two ways to do that. One is, of course, we can use the temperature of the inlet that is coming from the upstream unit processes, or it can be defined by the user. For example, if you want to change the temperature that is coming from the previous unit process, you can do that too. The other thing is the model has been built around in such a way that the temperature is specified, the drying temperature is specified by the user, and also the expected dry solid content that is desired, and also the thermal efficiency factor. And this is the factor that actually probably would be different for different technologies that are there for drying solids. The other information that we need is with respect to the thermal properties of different substances that are going in to the dryer, for example, water, inorganic solids, organic solids. So all those thermal properties of those components is used in creating energy balance, and to estimate how much of the energy will be required for getting to the desired dry solid concentration given a specific feed sludge property. So the application of the model, if we think about it, is the focus is not really to design or not really to kind of design an equipment, but more like to analyze various process configurations in which you would like to know what is the energy requirement, for example, for drying under certain conditions. So we can do an external energy calculations there, or otherwise we can look at some of the alternative evaluations. If you have different options that you want to evaluate with respect to dewatering efficiencies, then you can easily put together a model where you can have different dewatering efficiencies, and then see can run a kind of a cost benefit analysis with respect to how much what is the kind of a combined system that might be the most cost economical for doing dewatering and drying, so you can do those kind of things. The other things are sometimes we want to reutilize the biogas that is coming out from anaerobic digestion. So in fact, that is a very viable option, and we want to look at how much biogas is being produced and whether the energy that will be created by biogas can be used for drying. So those kind of process feasibility studies can be done in a very systematic way using this process simulator with the drying object. So now I would like to give you an example, basically just to show you some of the inputs, some of the outputs, and also show you some of the sensitivity analysis that we can do in GPSX. So this is a very typical layout, and normally without a drying and the incinerator object, we would have made this layout up to anaerobic digestion and dewatering, but now you can extend the your analysis by including this drying and incinerator unit processes. So let's look at the layout that we have. So this is GPSX layout that we have here. So in this case, basically we have a liquid train, and the solid is we are getting primary solids and the secondary solids which are being thickened and going to anaerobic digester, and having a dewatering step, and that is being fed to the drying unit process here. And so if I run so as I said that we need the feed sludge characterization here. So in this particular case, whatever the sludge properties are being calculated by the model, depending on the process operating condition in the upstream side of the treatment plant, those properties will be passed on to the drying unit process with respect to, for example, the organics, inorganics, and all the ammonia and all the soluble compounds that will be passed on to this particular unit process. So if we run this particular model, and this is just a steady state analysis, and we can see various type of outputs that are being produced by the model. So let's look at the drawing here, and we can see that the flow that is coming in for the sludge is 6.2 ton, and after drying it becomes 2.5 tons. So it's doing the volume reduction. At the same time, the incoming solids are 30%, which is the dewatering efficiency of the dewatering machine, and we are drying it to up to 80% here. And correspondingly, all the other, the properties of different various properties are being calculated for the dried sludge here. Some of the other key indicators that we normally want to see with respect to drying operations, they are also available on this particular panel here. So we can look at, I talked about calorific value. So if we look at the calorific value of our feed sludge, that is only 3,205 because there is a lot of water. But after drying, the calorific value of the sludge goes up to 8,547 megajoules. So also, if you are designing drying, then the specification for dryer should be that you need to remove about 4,000 kilogram per day of water. So that should be some of the specifications. The other things that are being calculated by the model is how much of the heat is required per unit dry solid, per unit water evaporated, and these are some of the benchmarks that you can compare among different technologies to see whether you're getting the best energy efficient technology in your plant. So you can do all of those stuff here. Now, the second example that I wanted to show you is with respect to how the energy requirement changes basically if we were to choose different dewatering machines here. So in this particular case, if I look at dryer variables here, so this is energy required that is required for drying. So I want to essentially look at basically how, if I want to, for example, if my dewatering machine is producing 30% dry solids, then if I want to get to, for example, from a 40% to 90% drying sludge, how much energy I would need. So if I want to conduct that kind of an analysis, then I can run a sensitivity analysis in GPSX. And just to do that, basically I'll turn on the analyze mode, which means that we are going to be running a dry solid content from the dryer from 40 to 90% when my dewatering machine is achieving 30% total solids. So let's just run that and see what happens. So it'll take a little bit of a time there, but pretty quick. So we can see that how is my energy demand. Basically it changes when I want to go from 40% to 90% when my dewatering machine is producing 30%. So it's a quick way basically to find out how much energy you will consume and how much energy you would need actually to get to what stage. So this is really important, because if I were to look at my digester and see if I were to see how much of my my energy that is being produced from the digester and how much excess energy I have. So in this particular case, I have about 300 and I'm consuming 100 for digester heating. So I have about 183. That's the number. If I subtract these two things, that is an excess energy that I have from anaerobic digester. So what I can do is I can look at 183 here and see how far can I go with respect to my drying of my solids. So this is really useful, but at the same time, I can also run an analysis where my dewatering efficiency is gone down from 30% to 20%. And if I run another analysis in the same way, I will get to another graph, and I will see that probably if I just want to use my excess energy from anaerobic digester, I may not be able to dry my sludge in a very efficient way or to a high percentage. So so this is analysis, and if I were to show you the kind of the outputs, basically, if we were to just collect the outputs. So if I were to look at that, so when we have a dewatering, that is dewatering is done at 30%, then this is energy required for me, and this is excess heat from the biogas. So I can see that my excess heat actually can help me get to a very high dry solid content in the dryer. But if I were to look at if my dewater sludge was only 20%, then I can see that by using this excess heat, I'll be only able to get to 50%. So this is just an example of how you can use the model, dryer model. And of course, this is just one type of analysis. You can actually use some other kind of PID controllers and other stuff, and you can run multiple analyses in many different ways. So now we would like to get to our next unit process, which is incineration. And incineration, as you know, it's a thermal combustion that leads to complete oxidation of organics that are being fed to the incinerator. And typically we have seen, incinerators, prior to incineration, there will be a drying step. So that's kind of very typical, because you don't want to feed very wet sludge. That reduces the efficiency of incineration. The operating costs are typically reported to be high for incinerators, so that's why it's not a kind of the first option for people to use. But at the same time, if you're using it with energy recovery, then it becomes an attractive option. And sometimes if you don't have any other disposal routes, then this is probably sometimes the only option available to the plants. So in this particular case, if we look at the model, it's essentially the same thing. We have one feed coming in, and then we have two outputs. One is representative of the flue gas, and the other one is the ash that is coming out from the incinerator. In this particular case, again, the same thing. All the input properties, they can be transmitted from the upstream unit processes. Like if we have a dryer, so we are already calculating all of these calculations we are doing for the feed sludge, and that can directly get fed to the incinerator. So in addition, we have for the incineration, we need to put extra air, or there has to be an air source, so that there is an oxidative combustion, and all the organic material is converted into CO2 and stuff like that. And sometimes, depending on what temperature do we want to keep in the digester, we need to feed an outside fuel. So there might be a need for a fuel that needs to be fed to these incinerators. What happens inside this is essentially all the carbon that is coming in gets converted into CO2. The nitrogen, some of the nitrogen from the air, it can come out as nitrogen gas. Some of it may get oxidized to some of the NOx compounds. Hydrogen that is there in the organic compounds get converted into water vapor, and the moisture also gets evaporated to water vapor. So these are some of the reactions, and of course there are many other reactions, complex chemistry that is going on inside. But from our process simulation point of view, these are the major things that we are considering inside the model. Again, here what we are trying to do is we are trying to create a mass balance with respect to all the feeds that are coming in. So we have mass of the solids that are coming in, mass of the air, mass of the fuel, and all of this mass has to get either converted to the flue gas or it remains as ash. So in this particular case, the mass of the solids are known. The fuel is provided by we can calculate it based on the requirement of the temperature, but this could also be an input to the model. So it could be a calculated variable or an estimated variable. Also, this one is an estimated variable, and these are all masses of the flue gas and masses of the ash are calculated by the model for you. Again, the energy balance, same thing. Basically, other than the thermal energies that we had for the dryer, there are two other sources of energy that we are taking into account. One is, of course, you have solids. So when you do thermal oxidation of carbon, you are releasing some energy, and that energy is being added to the balance here. And also when you're adding the fuel, then that fuel is also producing some energy, and all that energy is being taken into account into the mass balance. And ultimate goal of this equation is to estimate the temperature, the operating temperature that is there in the incinerator. So just to show you some of the inputs that are required for, or the process variable that are required for incinerator unit process, we need information on the reference temperatures. That is just to create the mass balance, we need the reference temperatures of the feed solid, reference temperature of the feed here, and then we need the ambient temperature as well to estimate the losses between inside, based on the inside temperature of the incinerator and the outside temperature. So those are some of the inputs that we need for temperature. The other things are related to incineration operation. And the things that we are expecting here is fuel supply rate. So like I said, you can add a fuel supply here, or otherwise we can use a PID controller and we can estimate the fuel supply from the model for a given temperature. So if fuel supply is provided, then we are estimating temperature, but if the temperature is providing, then we can also estimate the fuel supply rate. So we can go either way in the model. The other thing that we need is, just by default, we are using natural gas as a source of energy or source of fuel in the model. Then you need to also specify excess air supply. So as we know, we need excess air, otherwise the incinerators probably don't have enough oxygen and it won't work. So there is an excess air supply demand that is required, and that is a user input here. Some other inputs with respect to just providing a flexibility with respect to unburnt carbon in ash residue, and also to look at some of the ash that can get carried over by the flue gas. So those are the percentages that we have. Some of the other parameter is the heat loss coefficient, which essentially depends on what type of incinerator unit process you're using, and probably can be provided by the vendors. The other parameters are with respect to the thermal properties of different components. So specific heat of water, latent heat of water, and all these parameters are being used in the model to estimate, to create a mass balance of different components there for the energy. So now, again, we would like to give you a demonstration of this incineration, show you some of the outputs and understand the mass and energy balances. And I will also run a couple of other analyses where for a given temperature, for example, like I said, if you give a temperature, then we can estimate the fuel consumption as a function of drying efficiency. So we can do kind of many things there. The other analysis that we can run is that we give for a given drying efficiency, we can estimate fuel requirement to achieve a different temperature. So I'll show you with the layout for these three things. And first of all, I mean, let's just run a simple analysis and look at how. Yeah, this is the layout. So we'll just run a simple analysis, the same layout, and in this particular case, we will just focus on incinerator, and we'll show you what are the sorry. So I think I have to turn off our sensitivity analyzer first, and run an analysis here. So this is just a steady state analysis, and we will look at some of the incinerator variables here. So you can see that there is so much of 2.353 ton of material is coming into the digester here, and the total solids that are coming in, and the total solids is actually includes some of the inorganics that are in the soluble phase. So those are being included here. Total suspended solids, because our dryer was producing 80% dry solids, so that's the solids coming here. So all of those properties are being fed into this incineration unit process. And based on the current operation, when we didn't have any fuel, so here we didn't have any fuel input, we are estimating that we will only be able to achieve a temperature of 600 degrees C if we don't use any fuel there. So there's a mass flow 0. And then how much of the mass of oxygen that we need, how much of the air supply we need, fuel to feed ratio, feed loading rate. So it provides you quite a lot of information that is typically used by process engineers to kind of make some decisions on the process side. One of the other information that you will see here is that it can provide you with the information about what is the oxygen fraction in your flue gas. So right now we're estimating 12.43%, and sometimes this is a control variable that is used in controlling the incinerators with respect to feeding, how much oxygen you are feeding. So sometimes you want to achieve, like, you don't want to overfeed or you don't want to waste air, you want to economize on that. So there is a possibility to create some controllers around using the percentage of oxygen in flue gas and your oxygen supply. So you can do all of that stuff. There are many other outputs that are available for you to look at. So if we look at, we can actually look at with respect to the inputs, like how much are the inputs that are going in and how much are the outputs that are coming out. So here, if we look at the input of total mass that is coming in and compare it to output of the total mass, then we see that they are exactly matching, which means the mass balance is good. And then also provides you with respect to the flue gas composition, as I was talking about, and also the ash composition. So in this particular case, since the model only has certain elements in it, like calcium, magnesium, potassium, phosphorus. So all of those compounds we can calculate that will go into the ash, but there are some unaccounted inorganic substances that come or that are there, and they are not really elementally, their elemental composition is not well defined. So those compounds are just calculated in the model as unaccounted element in ash, which is actually a very large fraction. So you get all of that information from the incinerator unit process here. Now let's look at our two other analyses that I was talking about, and the first one is with respect to a temperature control. And in this particular case, we are setting the temperature that we want to achieve in the incinerator at 800 degrees C using a PID controller, and the PID controller is on. And I want to look at what is the effect of my dryer performance on the fuel requirement that I will need to achieve a temperature of 800 degrees C. So there is a graph here that is representative of incinerator temperature and the fuel consumption that will go. So we'll again do a analysis on the analyze mode. So this is a sensitivity analysis feature. Can run the model with different dried sludge content here, and then it can estimate how much is the fuel requirement and how much will be the kind of fuel consumption that we will need. So as we see that as we increase the dry solid content from the drying, our fuel requirements keep on going down. We still maintain our temperature of 800 degrees C, but drying can actually reduce the fuel consumption that will be needed to achieve the same temperature in the thing. But of course, when we want to go to the higher drying, then we are also actually needing more energy here. So essentially what we can do is we can combine this to energy and run this sensitivity analysis, which could actually be an optimization exercise, and try to find out what is the best drawing efficiency that will lead to the minimum energy consumption. So we can do those kind of things with this particular layout. So the other layout that we have is, I wanted to show you, is having an incinerator, and in this particular case, trying to fix our dryer efficiency at 80%, but looking at what will be the fuel requirement if I want to operate my incinerator between these temperatures. And this is kind of a little bit hypothetical exercise, but it kind of conveys the point that you can do this kind of analysis. So let's look at this, and then we are going to go to analyze mode. And again, we are going to run an analysis from 500 to 1000 temperature of the set point control variable, and then we'll see how much fuel we will need. So this is another analysis that we are going to do. It may take a few seconds here. So you can see that initially our temperature is kind of 578. So we started with 500, which means that without any fuel, like I said earlier, we are able to achieve 578. So there is no fuel requirement. But as we kind of increase our temperature, our fuel requirement starts to go up. So this is a kind of a quick way to actually estimate the fuel consumption requirement, how much, what temperature you want to run your incinerator at, how much fuel you will need. And in fact, since we are running a process model, what happens if there is something changes, like if we remove our primary settler, take all of the sludge to secondary aeration tank, the makeup of that sludge is going to change, and some of the changes will then get propagated to all the drying and incinerator unit processes and may have some effect on the energy consumption in the process. We come back to our slideshow here, and so we have done the demo, and just wanted to summarize what we talked about today. So the unit processes of sludge drying and incineration allows users to include various sludge treatment alternatives in process model, which is really a great extension of the techniques that we have in simulation in GPSX. It just extends the capability and lets you do more analysis with respect to the downside processing of the solids using dryer and incinerator unit processes. The other thing is, of course, as I showed you, that you can quickly develop strategies for energy reuse, recovery across various treatment units. So you can also look at if it is a high quality energy, for example, or it is a low quality energy, and actually, in fact, you can do some kind of, you can use a high quality energy and then degrade it to low quality energy and then use it for further low quality energy. What I mean to say is you can use, for example, the gases which are very high in temperature. You can use, in fact, those drying gases for drying your sludge also. So those kind of strategies can be actually looked at in a very holistic sense by putting together all these different alternatives. The other benefit of doing using integrating this with the process models is that you can estimate the water quality and the sludge quality at various stages of the process. So no information is getting lost. And the other aspect, of course, this is basically that all the feed properties are automatically adjusted with respect to mass and quality, which kind of reduce your input with reduce the uncertainties with respect to the inputs that you need to put into the model. So you don't really have to run some analysis somewhere, take that data and use that data in either let's say Excel sheet or some other simulators. You don't need to do that. It can be done at one place. So that's kind of I think one of the main advantages of incorporating these two unit processes in the simulator. So if you're curious, I mean, then there are some references. It's not an elaborate list, but some of the major one that we use for putting together this model for drawing and incinerator are provided in this list. And if you ever need them, just let us know and we can provide you some of these references.